students. Today I would like to explain how to design second type of coupling is bush pin type flexible coupling. So let us start with measure proportions, that is standard proportions. First important parameter is d suffix h, means outside diameter of hub. So students, this is nothing but the layout of flexible coupling. Here diameter dh, small dh, is nothing but the diameter of hub. Upper portion is nothing but hub and lower portion in the diagram is nothing but flange. So first important parameter is outside diameter of hub, and it is standard proportion of outside diameter of hub is nothing but 2 times diameter of shaft. This small d is nothing but diameter of shaft. Next, L suffix h, length of hub or effective length of key, that is LH equal to 1.5 times diameter of shaft. Here LH is nothing but length of hub, that is lower portion of, that is nothing but for flange. Then capital D is nothing but pitch circle diameter of pins. Here the capital D is nothing but pitch circle diameter of pins, and standard proportion for that pitch circle diameter is nothing but 3 times diameter of shaft to 4 times diameter of shaft. Then next, small t is nothing but thickness of output flange. Small t is nothing but thickness of output flange here, that is small t equal to 0.5 times diameter of shaft. Next important parameter is small t1 is nothing but thickness of protective rim. Small t1 is nothing but thickness of protective rim, that is t1 equal to 0.525 times diameter of shaft. Then small d1 is nothing but diameter of pin. In the diagram, small d1 is nothing but diameter of pin. Then next, d1 standard proportion for diameter of pin is equal to 0.5 times diameter of shaft upon under root of n, where under root of where this n is nothing but number of pins and d we know that is diameter of shaft. Then it is also concluded that in analysis of flexible coupling, it is assumed that the power is transmitted by the shear resistance of the pins as the flange on the input shaft rotates. It exerts a force P on each rubber bush. In the layout, the upper portion is nothing but pins, brass linings, that is on the outer portion of the bolts, rubber bush are there. So next important parameter or next is resisting forces in the rubber bushes. We know that torque is equal to force into radius. Similar way, here we apply one equation mt, that is torque, torsional moment or torque equal to force P into radius, here it is d by 2 into number of pins, where mt we know that is nothing but torque transmitted by the coupling in Newton mm. Then next, P, that is force acting on each rubber bush or pin in terms of Newton. Capital D, pitch circle diameter of bushes or pins, that we have already discussed, and number of bushes or pins. Then next, the projected area of the rubber bush is shown in figure. In the figure, the projected area is given for bush linings. So the force P is equal to the product of the projected area and the intensity of pressure, that is capital P equal to capital dB LB into PM, where dB is nothing but outer diameter of bush. Here in diagram, dB is nothing but outer diameter of that bush, and LB effective length of the bush in contact with the input flange. PM permissible intensity of pressure between the flange and the rubber bush, that is in terms of Newton per mm square. So from equation A and B, equation A is mt equal to P into d by 2 into n, and equation B is P equal to dBLB into PM. That is, by just evaluating these two equations, we get mt equal to dBLB PM into d by 2 into n, that is mt equal to 1 half PM dBLB capital D into n. Next, call this equation as equation number C. The permissible intensity of pressure between the rubber bush and the cast iron flange is usually 1 Newton per mm square, that is equal to P suffix m. Also assume ratio of effective length of bush to the outer diameter of bush, that is LB upon dB equal to 1. Substitute this equation D in equation C. By substituting, we have mt equal to 1 half of PM into dB into, here LB is nothing but dB into D capital D into n, that is mt equal to 1 half of 1 equal into dB square into capital D into n, because PM is equal to 1 Newton per mm square. Then next, mt equal to 1 half dB square dn. By evaluating this equation, we have mt equal to 1 half dB square d into n. The outer diameter of rubber bush is obtained by the above equation. Then next, direct shear stress in the pin. We know that direct shear stress tau equal to P upon area pi by 4 d1 square. From equation A and F, equation A is mt equal to P into d by 2 into n, and equation F is tau equal to P upon pi by 4 d1 square, that is tau equal to 2. I just put equation of P, that is equal to 2 mt upon dn, that is 2 mt upon d1 into 4 upon pi d1 square, that is tau equal to 8 mt upon pi d1 square into capital D into n. So this is about some important parameters and equation used to design flexible bush pin type of coupling. Then next important factor or next important point is design procedure for flexible coupling. While designing flexible coupling, first important parameter is shaft diameter. We have to first find the diameter of shaft. We have power equation P equal to 2 pi n mt upon 16 into 10 raised to 3, and shear stress for shaft, we know that is nothing but 16 mt upon pi d cube. By using these two equations, find diameter of shaft. The next important parameter or factor is dimensions of flanges. We know that dh is equal to 2d, lh equal to 1.5d, d equal to 3d to 4d, t equal to 0.5d, t1 equal to 0.25d, that we have already discussed. Next important parameter is torsional shear stress in the hub. Hub is under torsional shear stress. It can be calculated by considering it as a hollow shaft subjected to torsional moment mt. The inner and outer diameter of hub are d and dh respectively. Tau equal to mt r by j, that is standard equation. J is nothing but polar moment of inertia pi by 32 dh raised to 4 minus d raised to 4, and r radius is nothing but dh by 2. Next important parameter is the shear stress in the flange at the junction with the hub is calculated by mt equal to 1 half pi dh square t into tau. Then diameter of pins, number of pins usually 4 to 6, that is diameter of pins d1 equal to 0.5d upon under root n. Determine the shear stress in the pins by using equation tau shear stress equal to 8 mt upon pi d1 square d into n. The shear stress calculated by the above equation should be less than 35 Newton per mm square, that is, or this is a standard proportion for shear stress. Also determine the bending stresses in the pins and confirm that it is within limit or not. We have bending stress equal to 32 MB upon pi small d1 cube. Next important parameter is dimensions of bushes. Calculate the outer diameter of rubber bush pi using equation mt equal to 1 half db square d into n. Then next calculate the effective length of the rubber bush pi lb equal to db. Dimensions of keys for flat key use width b equal to d by 4, that is diameter of shaft by 4, and height h equal to d by 6 and length l equal to length of hub. With these dimensions of the key, check the shear and compressive stresses in the key by using equation shear stress tau equal to 2 mt upon dbl and sigma c equal to 4 mt upon dhl. So this is about the important parameters to design flexible type bush pin coupling and the design procedure or design equations used to design flexible bush pin type of couplings. Thank you, students.